So hello, my name is Vanessa and I'm here to present our paper about automatic spatial calibration of near-field MIMO radar with respect to optical depth sensors. So let's start with a little bit of motivation why we are doing that. Multimodal sensor fusion takes a crucial role in self-driving cars to robustly navigate in their environment. And oftentimes these systems involve a LiDAR sensor and a radar, which both have complementary strengths to each other. For instance, LiDAR provides high-quality reconstructions and is more closely related to human vision, whereas radar is insensitive to environmental lighting and adverse weather conditions as the signal penetrates fog, dust, and also fabric, for example. So because these systems have proven to be already very successful in the far field, we ask ourselves the question whether a similar system can be employed in the near field as well. So the goal of our work is to spatially fuse the data of an optical depth sensor, in our case an RGBD camera, and a MIMO imaging radar in the near field. And to achieve this goal, a respective near-field sensor calibration is required. Now, if you're more interested in far-range applications, be aware that the term near-field thereby not only means that the target is placed very close to the sensor, like this is the case in our work for now, but in fact, with the increasing trend towards higher resolution radars, the radar antenna apertures will become larger and thus radars will more frequently operate in their near field as well. To achieve spatial sensor fusion, many related approaches in the far field utilize calibration targets for that. And in these targets, certain feature points are detected from both sensors, and then their transformation between each other is determined such that the respective sensor coordinate systems can be related to each other. Unfortunately, traditional far-field calibrations that use a corner reflector as calibration targets are not applicable in our approach. As can be seen, there is no easy way to locate feature points in the corner reflector in near-field radar reconstructions. Instead, our contribution makes use of a custom calibration target specifically designed for near-field radars. And in the following, I will now explain the design choices of the target as well as the methods how to localize the feature points in the camera as well as in the radar. So first of all, this is the sensor setup that we are dealing with. It consists of the bespoke MIMO imaging radar, as well as two optical systems that we calibrated in our experiments. One optical system is a multi-view stereo system of 5 DSLR cameras, where the reconstruction quality heavily depends on the amount of visual features of the target. The other system is Microsoft's time-of-flight camera that doesn't need visual features, but we have to deal with more noise in the reconstructions. Our calibration target is depicted on the left, and it consists of 4 styrofoam spheres that are visually colored and textured so that they can be easily detected in optical sensors. And inside these spheres, as well as in the center of the styrofoam board where they are mounted, there are tiny metal spheres implanted, which can be detected in the radar reconstructions. We chose this target design due to multiple reasons. First, we chose spheres due to their view independency. Second, we chose to wrap the metal spheres inside something else, which in this case is styrofoam, since metal in fact is highly reflective, which is good for radar reconstructions, but it delivers very bad reconstructions in optical sensors. And the material that we use here is styrofoam because styrofoam is nearly invisible for radar, so the radar sees the metal spheres inside, whereas the optical sensor sees the outer styrofoam spheres. Third, we chose to make those metal spheres especially tiny, very close to point targets, as the larger the metal spheres would be, the more distorted the radar signal gets, which makes it very challenging to locate a very specific feature point in that. So this is essentially the same problem that we also have with corner reflectors. Lastly, we use a symmetric sphere setup that is approximately the same size as the antenna aperture, and it gives us the possibility to apply prior knowledge in order to find the calibration target inside the sensor reconstructions. Furthermore, the symmetry ensures that the systematic noise that is present in the radar reconstructions, for example due to antenna side lobes, is also symmetric as well. So with this calibration target, we now aim to find the metal spheres in both the optical and the radar sensor coordinate system, So let's get into detail how the calibration target is detected in optical sensors. First of all, we detect the four styrofoam spheres by using their unique color features, and then we minimize an energy term in order to locate their respective sphere centers C. In this energy term, the center position C is enforced to have a very specific radius r with respect to the partially reconstructed sphere surface S. The radius is known in advance because we know the size of the spheres of our calibration target. So after optimization, these detected sphere centers should now lie exactly at the positions where the metal spheres for the radar sensor are positioned. So let's look at the localization procedure from the radar point of view. As previously mentioned, the metal spheres lie inside the styrofoam spheres, and in the first step they are detected together with lots of other point candidates based on their signal intensity that we receive. Because we already have a list of candidates, we do not explicitly optimize the sphere position this time, but instead we aim to locate the spheres inside this candidate list via a brute force optimization. And we do this again according to some energy terms. First of all points should lie on a common plane, which is estimated along the currently selected candidates and is parameterized by an offset and a normal vector. This plane is utilized to incorporate further energy constraints that describe the correct sphere positions. For the same reason, we utilize the fifth metal sphere in the center as an anchor point. And similar to the metal spheres, this anchor point is selected from candidates during the optimization. So with the plane and with the anchor point, we enforce additional constraints, which I will now describe in more detail. First of all, the L-sphere term requires the spheres to have a certain distance from each other, which again we know in advance because we designed the calibration target. Second, the L-plane term enforces a certain distance between the metal spheres implanted and the anchor point, which lies on the board on which the spheres are mounted. And lastly, the L-anchor term ensures that the projected anchor point onto the plane lies in the center of all implanted metal spheres. And so with that, we successfully located all feature points in both sensor coordinate systems. So the last step that remains is to register the detected metal spheres against the styrofoam sphere centers. And during this registration, we aim to find the optimal rotation r and translation t that aligns both sensor coordinate systems such that we can get a result like this here, where we can even verify that the central anchor point of the radar reconstruction overlaps with the optical reconstruction. We evaluate our calibration with the two different sensor setups, which essentially differ in the optical part. So we have a time-of-flight radar calibration and a multi-view stereo calibration. And then we repeat the calibration process from multiple positions and orientations of our calibration target, and then capture a separate object from which we measure the chamfer distance between the calibrated reconstructions. In the results, we can show that the calibration target does not have to be precisely positioned, but it's rather flexible with respect to its sensor distance and orientation to the sensor, such that we can achieve an average calibration error of around 1 to 2 millimeters, and also note that the sensor noise is still included in this remaining error. The reason why the calibration quality degrades at 50 centimeter target distance is because the evaluation object is always measured at 30 centimeters. And from that we conclude that our calibration is distance dependent, and this is mainly due to perspective distortions of optical sensors, which essentially limit the highest accuracy to a small spatial region. To anyone who is interested in more details and further experiments, we encourage you to read our paper. Finally, we show some visual results of the fused sensor data, and we can conclude that our spatial calibration is also visually very precise, even in the strong presence of radar noise, which arises in the reconstructions. To summarize, we made the following contributions. First, we built a custom calibration target that is specifically for the near field and is especially targeting high-resolution MIMO imaging radars. And then we developed a completely automatic pipeline that localizes the target in optical and radar sensors and registers the detected features with each other. Despite all the noisiness that is particularly present in the sensor data, our framework achieves calibration errors in millimeter range. And with that, I'd like to conclude my presentation. Thank you very much for your attention. Feel free to reach out and, of course, check out our paper. Thank you very much.